Good evening and welcome to tonight's lecture. I'm George Kraw here with Raphael Shannon Kraw. This evening we'll be hearing from Professor Emily Brodsky about a very very immediate item, earthquakes, something that affects all of us as Californians, but as we've seen, is something that threatens many places in the world, as the events in Taiwan have shown. Professor Brodsky has a PhD from Caltech. She came to UC Santa Cruz in 2006. We've been lucky to have her. Since that time, she has more awards and citations than I can list here. And just last year, she was elected to the National Academy of Science. Before we start the lecture tonight, I wanted to go over how we'd be handling the questions because it'll be a little different how we usually do it. Professor Brodsky likes to have questions during the course of the lecture. So if you have a question, raise your hand and Rafe will bring a microphone to you. But please don't start speaking until you get the microphone so those watching online can see this. For those of you online, you can ask your questions in the chat and we'll ask those at the end of the lecture. So now I'll turn it over to Professor Brodsky.
Thank you for inviting me. Thank you for coming. And thanks for accommodating my requests there. I get a little bored if it's just me talking. I'm going to talk to you today about earthquakes. And I'm going to talk to you about the earthquake problem. So I guess the first question is, what is the earthquake problem exactly? Thanks for coming even with the vague title. I think most people would think that the earthquake problem is some version of when will we have earthquakes. Well, I mean, more colloquially, it's when's the big one, right? That's the earthquake problem. That's what presumably most of you want to know. It's what everybody in my life wants to know. It's why I don't introduce what I do to the person next to me on an airplane. That's the problem. And it's particularly important, as George just said, to us Californians because, this got a little washed out, but I think you can still see. We are here. Do I not have a pointer? No pointer? No pointer. Okay. We are here where the red X is, and we are sitting right this second between two major faults. And you can take a look at the scale bar on the bottom. So we're about, 13 miles-ish from the San Andreas and a little bit less from the Hayward Fault. And so I would say that us Northern Californians are very interested in when the big one's going to happen. And the last really big one here was 1906, which was the San Francisco earthquake. And when I say the San Francisco earthquake, I think most people imagine an earthquake in San Francisco very reasonably. But actually, the fault that slipped, when a fault that big slips, when an earthquake that big slips, it's not just slipping in one place. It slipped all the way from Mendocino County to Watsonville. That's the big one. And we'd like to know when it's going to happen. So just to be clear and control expectations, I'm not telling you that today. I don't know. If I knew, I would tell you. It wouldn't be a secret. But what I want to do is try to kind of frame for you how, as an earthquake scientist, I think about this problem and what reasonable things we can do to try to ask, when do we have earthquakes? When's it going to happen? And to do that, I'm going to go through 4 different approaches on the problem, 4 different ways to think about the earthquake problem, and now you know what the earthquake problem is. And the first one I'm going to talk to you about is perhaps distilling the earthquake problem to its simplest form, thinking about it, can I say like a physicist might think about it? That we model the earthquake using my little demo here as an interface, a fault, between two objects. So there's a little cartoon here, but I find it more interesting to deal with physical objects. So let us imagine my brick here is the North American plate. You've got a good imagination, right? And my doormat here on the other side is the Pacific plate, okay? And the interface between them is the fault. And so what happens in an earthquake is the mantle's convecting and moving the plates. And so here I am moving the North American plate. And the plate sort of stretches a little bit as it moves, like my bungee cord, a little bit of elasticity. But most of the time, the plate's always moving, always, always. A couple centimeters a year, always moving. But most of the time, the San Andreas fault is not moving, at least not up here in the north. And so it's being held closed by friction. Friction prevents it from moving, but eventually, you ready for it? That's it. That was it. That's the earthquake, right? Eventually, the plate motion stretches the cord enough that it overcomes the friction. The elastic stress overcomes the friction, and we have an earthquake. So what does that mean? That means if we're going to sort of take this kind of simplified, distilled, let me call it earthquakes in isolation, just a model system approach, what we need to understand is the motion of the plates, which we actually do understand to a large extent these days. We have great GPS sensors that can tell us how the plates are moving. And we also need to understand something about friction, right? Because friction is what determines when the plate moves. Earthquake people tend to be quite obsessed with friction. We can model the system as, in this simplest form, as stress accumulating in my bungee cord and building up to the strength of the fault, which is determined by the friction. And then when we overcome the friction, the earthquake happens. So if we knew the strength of the fault, if we knew the friction, we'd know when the earthquake was happening, at least if we knew when the last one was, to some extent. So this discussion boils down to, let's learn something about friction in order to understand something about earthquakes. So let's learn something about friction. What do we know about the friction of rocks? We are talking about faults in the earth, so we're interested in the friction of rocks. And people have been taking rocks into the lab and squishing them for as long as I've been alive. They take them into these big presses, and we have one of these here at Santa Cruz. I almost said here at Santa Cruz. I'm not in Santa Cruz, but come on down and visit. You can see my colleague Heather Savage's lab, and she squishes rocks. When we do this, we can measure what the shear strengths, that is, how hard you've got to pull it this way in the direction of motion is, relative to how much the fault is being pushed together, which I'll call the normal stress. So the basic thing about friction is that if I put 2 bricks on here, I increase the weight, it is harder to make it move. The friction goes up. So I had to pull that bungee cord more before I got my earthquake. And you're getting nervous that the bricks are going to fly at me sometime soon. Hasn't happened yet, all the years I've given this talk. There's always a first. So what we measure in the lab since 1978 has been called Byerle's Law. And like most laws in geology, it's more of a guideline than a law. But it says that most of the time, for most rocks, the shear stress, the force that you need to pull it parallel to the fault, is proportional to the normal stress with a coefficient of friction of 0.6. That's the slope of the line, 0.6. there are a few rocks there, some things that have funny clays in them, those little points at the bottom, don't look at them. Most of the line, it's 0.6. Please remember that number, okay? So, if we are able to know that the coefficient of friction is 0.6 of rocks, and we are able to measure the stress accumulation of faults, they'll eventually hit the 0.6, the static friction strength, and we should be able to predict earthquakes, right? Awesome. Well, also, in addition to knowing how strong they are at failure, we also kind of need to know how much stress is released in each earthquake, because otherwise we don't know where the system resets to for the next one. So we need to know the stress drop also. So static friction minus the dynamic friction. The dynamic friction is the friction while it's moving. Most things have friction less while they move than when they're not moving. And so we need to know that dynamic friction as well in order to know how much stress gets released. We'll call that the stress drop. And then we know everything. Then we're predicting earthquakes. Measuring the static friction has been done for 50 some odd years. Measuring the dynamic friction during an earthquake is harder. How are you going to do that exactly? Right? You're going to get into a fault and put your friction probe in there, and you're going to get there to figure out what its friction is during the earthquake. You would have to have gotten there before the earthquake, right? And put whatever thing, and then it would have to survive the earthquake. And of course, I've already said we can't predict earthquakes. So that seems like a hard problem. It is a hard problem. And it requires thinking a little bit out of the box about how to measure that dynamic friction. Any ideas? No? All right.
The speed at which?
Oh, I'm sorry.
Would it be the speed at which the Earth is moving?
Speed is definitely a part of it. And so maybe, and this has actually been an idea, is that if you could measure really close to the fault how fast it reacts on a seismometer, if you got a seismometer like really close to the fault, that would do it actually. It has sort of the same problem that you have to get the seismometer really close to it, but that's part of why people have drilled holes into the San Andreas and stuck seismometers in them. The seismometers tend not to not work for that long in those environments, but there's an engineering problem there. Yeah. I'm sorry, making you run.
Gotta run.
Can you measure it in the lab?
You can measure it in the lab, and it's hard. It's a hard experiment. But sort of force feedback systems caught up to the experiment effectively right around 2010-ish, between 2000 and 2010. And so you have to push hard on those rocks while spinning them fast. When people measure it in the lab, they find that the dynamic friction is much more variable than the static friction. It's no longer Byerlee's law or even Byerlee's guideline. It depends very much on which kind of rock you go in and what speed you're going, and if you have water there or don't have water there. It's kind of a mess. So we really want to do it on a real fault. So let me tell you what we did to measure it on a real fault. After the Tohoku earthquake, that's the big Japanese earthquake in 2011, some of you may remember the tsunami coming in from that earthquake. It's really a catastrophic earthquake for northern Japan. Magnitude 9 earthquake. 1906 I was telling you about, from Mendocino to Wattsville, that's an 8. This is a 9. It is in fact the largest instrumentally recorded slip during an earthquake ever, of any earthquake we know of. by the trench, way out in the ocean, where the ocean is deepest, and one plate is going under the other. The way the geometry of the plates work here is one goes under the other. It was probably 70 meters of slip over the course of about 10 minutes. So I don't know, how long is this room? Longer than this room, right? Of one side of the fault. So when I say slip, that's the brick moving 70 meters. So it was big. And that, after the earthquake, I think the Japanese government felt very obliged to, really obligated to learn as much as they could from this catastrophic event, that this was sort of a societal obligation, I think. And in particular, why it slipped so much out by the trench. And so a bunch of us organized the JFAST expedition, which was a deep sea drilling expedition to drill into the fault in the place where it had the largest slip. The idea was to go into the fault and take its temperature. So there's your answer. Why do we want to take its temperature? Well, it's just like rubbing your hands together to keep them warm. If you knew how many times you rubbed your hands back and forth and how hard you were pressing on your hands, you'd be able to take the temperature between your hands and measure the friction, right? We don't do this that much in California, but, think of those poor people on the East Coast. If you can measure the frictional heat dissipated between the faults, you get there fast enough after the earthquake, you stick some temperature sensors into the fault, you let them sit there and equilibrate for a while, make sure you're measuring the right thing, come back, pull them out, you'll get the friction. We got the friction. This technically, from an engineering point of view, was a huge challenge. Where the fault slipped the most was under 7 kilometers of water. Nobody had drilled a substantive hole of any kind below 7 kilometers of water before we did this, let alone a hole that was deep enough to penetrate the fault, that was instrumented, that recovered core, recovered rock from the fault. None of this had been done before. The only ship in the world that could do it happened to be owned by the Japanese government. It was called the Chikyu. It is still called the Chikyu. It's an amazing vessel. And so we did it. So what did we find? Yeah.
I was wondering if you expect to see a decline in temperature as the heat dissipates, and if you can extrapolate from that back to how much heat, whether that helps at all in the measurement.
We did expect to see a decline on temperature. The duration of time that the instruments were actually in there, actually mainly what we saw was a re-equilibration of the hole, because when you drill a hole, you dump cold seawater in it. And so it had to heat back up, and there was some limit to how long we could keep the instruments in there. And so we didn't really see that decline. This October, the Chikyu's going back, and we're looking for that decline. So first things first, this is what the fault rock looked like. So the Chikyu pulled out this kind of cruddy black gunk, very clay-rich rock. And my colleague Matakari took it to his lab in Bremen and measured the coefficient of friction on it, and it was 0.24. Anybody remember Bailey's law? 0.66. So already, this is the low speed, so the static coefficient of friction was much lower. I said it was gunky clay-rich. Ignore those clay-rich points on the plot. Apparently, they're important. The big big plate-bounding faults are actually very often filled with clay. and we shouldn't be ignoring them. So that was lesson 1. Then after the rock was recovered, the team took 55 temperature sensors, duct taped to a piece of climbing rope. Some of these very big multi-million-dollar projects at the end are not so glorious. It involved duct tape. And then they were stuck in the hole for 9 months and pulled out 9 months later. There's the team looking pretty happy because all 55 came back. They were autonomous sensors. The data was on flash drives under each roll of duct tape. So if the rope didn't come back, we had no data. So everybody was happy at that moment. This is what it looks like. So this is, to me, the exciting plot. Everybody else wants to see, the happy people on the ship. But this is the plot I care about, which is what you're looking at is depth. Each row is pretty much a sensor. And time on the x-axis. And the color is temperature. And I've taken out here the fact that the Earth just generally gets hotter as you get deeper. That's not that interesting in this context. So I've taken that effect out of this plot. And so what you see here, a couple things. First of all, you see the big red thing? That's the fault. That's the depth of the fault. That's the thing we're looking at. And anybody looking at the color bar? It's 1/3 of a degree. Yes. That's why we had to work so hard to find it. And in fact, people had tried to measure this on previous earthquakes that hadn't slipped as much and couldn't find it because it's small. That's already giving you a hint as what the answer is. You'll also notice in response to your question that the fault heats up over time, that it starts blue on the left and turns red on the right, and that's really because the fault needed to re-equilibrate from the cold seawater. So the cold seawater has to heat up, and we can model that effect. That's something we know how to model. And so we could compare this to a model given a certain friction on the fault. I think it's not terrible for a simple model on the right. And that gave us a coseismic, that means during the earthquake, friction coefficient of 0.08. Anybody remember Byerly's law? Okay, so even to a geophysicist, and we're notorious for having huge error bars, that number is a lot less than 0.6. So our conclusion here is that the friction during an earthquake is really a lot less than before an earthquake. And even before an earthquake, it was less than Byerly's law. So maybe Byerly's law really isn't even so much of a guideline. But these are the kinds of numbers we need to know to deal with the earthquake problem in isolation and start sort of a first principle approach to anticipating when earthquakes are going to happen. All right, well, that's cool. Well, I was about to move on, but go ahead.
You mentioned that this earthquake happened at 7 kilometers depth. So how does these number 800 to 820 meters relate to 7,000 meters?
Oh, I'm sorry. 7 kilometers of water depth, 820 below seafloor. My bad. Okay, yeah. Sorry, I should have been clearer there. Yeah, so you go through the 7 kilometers of water. You think it's easy to drill through water? It's not easy when your motor's in the ship. Okay, and you got the spaghetti string dangling below you that you're trying to control. But so you had to drill through 7 kilometers of water. I mean, not drill, but get the string through 7 kilometers of water, and then another 820 meters of rock. Okay, thanks for clarifying. And the rock is a pretty good blanket, which is why we're still able to see that 1/3 of a degree. It actually took us about 1.5 years to get out there, and then another 9 months. But because the rock's a good insulator, you can still see it. Okay. Okay, so I clearly love this data, right? You can tell, can't you? But I'd like to introduce my postdoc, Will Steinhardt, in the back of the room. He's helping out with the questions tonight. And the role of postdocs in the academic establishment is to prove their advisors wrong. So Will arrived a few years ago. You know, he began his postdoc in February 2020, which wasn't the best time to begin a postdoc. But he's persevered and is doing great. And what he has done is to build a laboratory experiment version of a fault in my lab in Santa Cruz. It's sort of a transparent rubber fault where you can, and it's very squishy, so that you can have some part of the fault slipping, but not the whole fault slipping, that it's soft enough. Unlike my brick, it's more like moving a carpet around, that you can have part of it slipping up, which is what real faults do. I said, you know, the magnitude 8 on the San Andreas went from Mendocino to Watsonville, but other earthquakes like Loma Prieta did a little section in the Santa Cruz Mountains. They don't always move the whole fault. So this laboratory apparatus can create that feature of not moving the whole fault. And he can make these beautiful movies of these earthquakes in the lab. It's awesome. You should talk to him about it after the talk. I'm just going to show the answer. What Will did was use this apparatus to measure the stress drop, that is the difference, what we thought was the difference between the static and the dynamic friction. That is the difference between the stress of the fault before the earthquake and after the earthquake for a whole bunch of lab experiments. And because it's a lab experiment and you don't have to just sit around and wait for Tohoku to move, he can do hundreds of these. And so there's a lot of information in this plot, but what I want to draw your attention to is something that really confused me, and I fought with him about it for quite some time before I decided that he might be right, which is that as he changed various conditions on the fault, the first thing that he did was do a bunch of earthquakes with different normal stress, that different weight on the fault, different number of bricks on the fault. And one of the few things we know about friction, friction's mysterious, friction's awesome, but one of the few things we know is that when you increase the weight of bricks here, then the frictional stress should get bigger, right? And so if it's really friction, then I should have to pull harder to make it go with the extra bricks. So he turns on the screw and increases the normal stress. It's like adding extra bricks. And also the amount of stress change during the earthquake should also increase, because both the static and the dynamic friction are proportional to the weight of the bricks, the load. So you've had enough of a chance to stare at this. These green stuff is all one condition, just a very simple setup with no bells or whistles, no extra little asperities, bumps on it. And he increases the normal stress, and this, you know, within statistical error, there's no change. So that's weird. That's not supposed to happen. So if we think that the stress drop of faults is governed by friction, like I said in my beautiful isolated slider block model, my physicist model of an earthquake, that's not supposed to happen. That's why you do experiments. And so he did it at a bunch of conditions. I'm sure he'd love to tell you about it after the talk. But the only way he could kind of break it, the only way he could get the stress drop to depend on the normal stress was actually to reduce the size of the sample, to cut it down. And when he did that, what he found is that if you made the sample small enough, suddenly stress drop started depending on normal stress again. And so what that was is when the sample was small enough that the fact that it was squishy didn't matter anymore. When the earthquakes are going all the way to the edge like they do in the bricks, then they start behaving like the bricks. And so the elasticity of the system mattered. The fact that you don't rupture the full fault every time matters. And if you do rupture the whole full fault, then you start behaving a little bit more like a frictional system. All right. I've come to terms with it. I'm good. So the idea here again was that frictional shear stress should be a coefficient of friction times the effective normal stress. And that is the sort of underpinning of this slider block model. And Will said no. And so how can this be? How can it be that the faults aren't really frictional after all? Well, we don't really have an answer to that yet, but I'm going to wave my hands a little wildly here and point out that faults are not homogeneous, uniform objects. They're rocks. They have bumps on them. They have little bits that are wider or thinner or stronger or weaker. They're a little bit more like a board being nailed together, where you have some strong spots and some weak spots. And so that heterogeneity matters. And if there is a particular distribution of nails, a particular spacing of nails, then you might actually be able to create a system that has these stress drops that no longer depend on how hard you're pushing on it, but just where the nails are. Oh, well, that's bad news. That's a more complicated system. That's the end of the line for the physicists. Let's move on. Let's deal with earthquakes on heterogeneous faults, faults that have bumps and warts and interesting things on them. This is the domain of the geologist. Let's deal with earthquakes as geologists. So I don't know how many of you have ever seen a fault. There's a fault surface. This is a fault surface in Oregon, and a quarry we used to like to work in a lot. This is actually one side of the fault. So the fault slipped this way, and that wall is what's left on one side. And circa 2008, I got this brand new exciting instrument called a ground-based LiDAR. It's awesome. And took measurements of the surface of the fault and walked away with a digital elevation model of the surface of the fault and measured all those bumps, all those heterogeneities, the roughness. And what did we learn from that? We learned that different faults are different. It matters how much a fault slips. As a fault slips, it gets smoother and smoother and smoother. And looking at that digital data, we can statistically show that, going from Mount St. Helens, that's a volcano, not a fault, right? But there was an edge of a spine of lava that got extruded there that was like the brand new, freshest, most baby fault you've ever seen. And so my student and postdoc helicoptered in, and they had a good time taking this data. And all the way on up through the San Andreas, and they get smoother and smoother and smoother. So faults, as they mature, they get smoother. And we can measure that also on maps of faults on the surface, from very immature faults, which not only are rougher on their surfaces, but also have lots of little extra splay faults, secondary faults. It's more like a family of faults. And then they get somewhat smoother as they mature. Very recently, my student, Weiyong Gao, has looked at how these geological features of faults might be manifested in earthquakes. After all, what was the earthquake problem? When are the earthquakes happening, right? That's the earthquake problem. How do we use this geological information to say something about earthquakes? And so what you can do is compare earthquakes on faults of different maturities and say, is there anything different about what's happening in the earthquake that you can predict based on these geological things you can observe? And she found that the smoother faults rupture faster, they slip faster. That actually was, to a large extent, known before. She said it more nicely with more data, but I think it was basically known. But she also pointed out that, the earthquakes on the immature faults had more aftershocks for a given magnitude earthquake than the ones of the more mature faults. The smoother ones So if you have a magnitude 7 on a smooth fault, it makes fewer aftershocks than if you have a magnitude 7 on an immature fault. Now we're talking, right? This is the earthquake problem. All right, fine, they're aftershocks, but you wanted to know about the main shock. But still, that's telling you some information about when earthquakes are happening. And there are differences in the behavior that we might expect based on these geological observables. It's also suggesting that just sort of becoming a geologist is not enough, that it's a fault system, it's a population of faults. It's not really just one fault, and we can't just be measuring the roughness of one fault. We need to go a little further than that. Yep.
Thank you. So what you're talking about with the sponginess of the rocks and then the maturity, I wonder, do any of the short-term changes, like how much it rains or droughts and how dry the ground's been, also come into it, so that you have to factor all of that into the calculations as well?
My life is complicated. In general, for the most part, we don't think that the weather penetrates deep enough to affect where the earthquakes start. Okay. For the most part. Now, you see I'm saying that very carefully. So usually earthquakes begin 5 to 10 kilometers, at least under the crust, and the water's only going down through the couple hundred meters. Okay. So in general, no. Okay. There are exceptions. For instance, the drought. The fact that the Central Valley pumped really a lot of groundwater out during the drought did affect the weight of the water on the crust of California, and that did affect the San Andreas.
Got it. Okay.
That's really wonderful work from Roland Bergman's group at Berkeley. It's an impressive signal.
Great. Thank you.
It had the effect of making earthquakes happen more easily then, because it's reducing the amount of friction?
In different places. It sort of, the parts that were being pushed on sort of got redistributed. I'm not sure it was more easily, but certainly you have to do the geometry. Okay. So we have a population of faults that are making earthquakes, and we're able to say something sensible about the aftershock production. That's sort of suggesting another angle, another approach on the earthquake problem. Let's start thinking about earthquakes in a fault system rather than on a fault. And let's start thinking about this instead of as a physicist or a geologist, as a statistician. Okay? That maybe there's something sensible we can say, statistically speaking, taking a large population of earthquakes, about, given an earthquake, how many aftershocks is it going to make? In fact, there are very sensible things we could say about that. We have really robust statistical laws. All right, they're geological laws, but we'll call them laws. But about, given a certain magnitude earthquake, how many aftershocks on average it's likely to produce. There are variations around that for geological reasons that we just suggested, but in general, magnitude 7 earthquakes make 10 times more aftershocks than magnitude 6s, and magnitude 6s make 10 times more aftershocks than at magnitude 5s. We also have statistical laws that we know about how rapidly that aftershock sequence dies away. It goes back to background. That's called Omari's law. We also know, in general, the population of earthquakes on this planet, there are way more little ones than big ones. There are 10 times as many magnitude 3s as 4s, 10 times as many 4s as 5s. Oh, no. Okay, if you string those statistical laws together, which is what Ogata did in 1988, that little diagram is supposed to be this sort of family tree of earthquakes that each one begets another one, begets another one. This is called the epidemic type aftershock sequence model. I think people are more familiar with this style of statistical model now, post-COVID, than they were before. It's exactly the same math. And it does really well. That statistical model, it's amazing how much of the earthquake catalog as we understand it that explains. It does awesome. Does everything except for the big ones. Oops, yeah, right. So everything except for the ones we really, really care about. But so, all right, it's a good starting place. And it's, for 30 years, it's been kind of the gold standard that it does so well. And so we've been really struggling at a statistical level to try to figure out what we could do to beat that. Here I am in Silicon Valley. I believe you probably have heard of the machine learning revolution. And so what can machine learning bring to this problem? What it can bring is sort of a more flexible, nuanced model that can go beyond this heavily parameterized 3 laws. And when we put in the key over the last 5-ish years, earthquake catalogs, their lists of earthquakes that we work with have gotten very much bigger. Partially, again, because of the machine learning revolution. I was telling you guys this on the phone. Before about 5-ish years ago, a little bit more than that now, in general, the way we detected earthquakes was a human being sat down with a seismogram and found the waves arriving. Okay? The rate limiting step was the labor. And so we are now capable of detecting earthquakes automatically. We now have million earthquake catalogs kind of routinely, and we can now ask those million earthquake catalogs using machine learning methods, again, what extra signal is there? Is there anything more that would be useful? And we're finally, just within the last year or two, moving beyond this statistical catalog. And so I'm finding this a very exciting time. I can tell you we finally beat ETAS, big news in my world. I can't yet tell you when the big ones are coming, but at least there's a strategy to move forward. This is getting better. The fact that earthquakes trigger each other also provides a window into physics, not just sort of empirical statistics. And you can really see this. This is the first seismogram I've dared to show you. It's not so scary. It's just a seismogram. It's just a measure of motion up and down on the Earth. And this one is, the top panel is from the Denali earthquake in 2002 as measured in Montana. The middle panel is exactly the same record, exactly the same file on my computer that I filtered to take away the long period waves that came all the way from Alaska and leave behind these little spiky things. The little spiky things are local earthquakes in Montana. They are very high frequency. They can't travel very far in the earth, those waves, so they must be local. They're beginning, as you can see, right when the waves from Alaska show up in Montana, 3,000 kilometers away. Earthquakes beget earthquakes. And in one of the ways they do it is through this ground shaking of one earthquake. We call this dynamic triggering, triggers other earthquakes. And we can now, it's such a beautiful, beautiful, robust observation. We can now use that as a tool to study faults in the earth. And it's, after all, the most robust feature, the thing we have the most predictability over is earthquakes trigger each other. That's what ETAS is all about. So let's see what we can do with it. What we can do with it is we can measure how many earthquakes each wave triggers, or we're being statisticians now. We take a big population of earthquakes around the globe that all hit the ground in California with the same ground motion, and we look sort of on average how many earthquakes get triggered. And so this is what my student Nicholas Vanderelst did as part of his PhD work, and it's kind of beautiful. If you hit the ground with a centimeter per second, you get sort of a 10% change of earthquake rate. If you hit it, you hit it. The earthquake hits it, not you. So if the waves from some distant big earthquake are big, they trigger lots of earthquakes, and if they're small, they trigger fewer earthquakes. And so what's that telling us? What it's telling us, I think, is something about how many faults are how far from failure in the earth. This is California data. So in California, if you hit it with a little teeny tiny wave, of that earthquake in Alaska sent some little teeny tiny wave down, then a few earthquakes get triggered, not many. And they're only the ones that were sitting somewhere on their earthquake cycle very, very close to that strength line. If, on the other hand, you hit it with a big wave, then almost all the faults get hit, because almost everything is that close to failure. And so by using dynamic triggering, we can measure the distribution of stresses in the crust. We can measure how many faults are at what stage in their cycle on average. And so it's a pretty powerful tool to start to get to at when earthquakes are going to happen. As a population, on average, we're being statisticians. Better, doing better, right? Can you get me doing better on the earthquake problem? But yeah.
How long does the stress stay before it's dissipated?
Oh, you know how to hit where it hurts. Great question. I'll repeat it because you didn't have the microphone. The question was, how long did the stress stay before it was dissipated? The answer is, in general, it's tens of seconds of that wave passing through. But the earthquakes are triggered sometime later. And you can really see that even in this figure, that the waves were there and then the little green arrows are all earthquakes that are triggered there later. We don't know why that happens. Earthquake science is fun. That delay is really a problem, that you shake it today and you have an earthquake tomorrow. It's clearly true. We don't know. We have ideas, but it's not well explained. So here we have managed to measure the number of faults within epsilon of failure within a system, with some small number of failure in a system, as a population. But I'm still not telling you when the big ones are happening. So let's try one final approach on the problem. Let's look at the earthquakes in a geological system. That is, let's recognize that, sure, we could do statistics on the whole population of faults, but they're not actually all the same. There are actual differences. It actually depends where on planet Earth the fault is. I'm going to call this approach geophysics. That we meld the geological and the physical insights. And to illustrate how important it is where the fault is, that's a terrible sentence, but I think you know what I mean. I'm going to just use this to illustrate this figure of a slow earthquake near Seattle in Puget Sound. So these are maps of the total slip on the fault. This is another one of those faults where one plate dives down below another. And these are the kinds of maps we typically produce for earthquakes. Except for instead of this slip happening over the few seconds or minutes of an earthquake, each of these frames is 1 day. So it's like an earthquake in slow motion. To me, this is one of the most important discoveries of earthquake science in the last 20 years. It's the discovery of slow earthquakes. That Earth, in certain places, not everywhere, that's why we have to put them in context, particularly in subduction zones where one plate dives below another, we have these slow motion earthquakes, and the faults are moving all the time. We don't have to sit around and wait for Tohoku, wait for the big earthquake to study it. We can measure stuff on a fault every single day. And that's huge. It's even better than that. This is another incredibly important observation made by Sergio Ruiz and his team in Chile, which is these slow slip events. All right, I want to say sometimes, but this time, there aren't a huge number of these observations, can happen before really big earthquakes. So this is before the magnitude 8.2 2014 Iquique earthquake. It's a northern Chile earthquake. You've possibly never heard of it, because unless you're an earthquake geek like me. But it's a real earthquake. It's 8.2. And over the weeks before that earthquake, the fault was moving slowly, and it went faster and faster and faster, and then the earthquake happened. Well, that's cool. That's what we want. Now, it did it before Iquique. It probably did it before Tohoku. In both cases, the data is a bit ambiguous, largely because these earthquakes are under the water, and that's not where, in general, our instruments are. For Tohoku, there were temporary instruments under the water, so we don't have a good baseline for it, but it looks like this sort of thing happened. For Iquique, the instruments were all on the coastline, and you're kind of trying to project what happened under the water. And so what we really want to do is figure out how common an observation this is. Is this something that happens a lot, or just before a few? I mean, certainly worth running after. Yep.
How much longer did you say before the earthquake does that slow slip happen?
In the case of Iquique, both cases, it was about 3 to 4 weeks. Okay, Iquique, it was also triggering a bunch of moderate-sized earthquakes, which in retrospect we call foreshocks. I mean, and everybody noticed them. My colleague Thorn Lay and I were sitting around we have coffee together every day, and we were sitting there at coffee saying, did it happen yet? Did it happen yet? I mean, it was clear. Now, I don't want to say we were predicting an earthquake. We weren't. But we knew enough about the geological context to know that a large earthquake was expected there, that was a fault likely late in its cycle, and this is the kind of thing that one might expect. And I have to say, our Chilean colleagues handled it beautifully. They really did a nice job of letting, publicly saying, look, everybody, there's a weird thing here. We don't know how to predict earthquakes. We're not predicting this. But just so you know, there's something a little bit odd that we don't know how to interpret. They did a fabulous job of getting that message out. To understand what might have happened there, I'm going to take you one last place in the world on this little tour. And that is Antarctica, to the Willans ice stream in Antarctica. Hang on, I'm supposed to be talking about earthquakes, and I'm now talking about ice streams and glaciers. But bear with me. Glaciers are just like earthquakes, where the rock is made out of ice. They're slipping, they have friction on the base. They're really very much the same kind of system, where the fault is between the ice and the rock. And the Willans ice stream in particular is phenomenal, because it has what are like slow earthquakes, 20-minute kind of earthquakes, every day. The way that ice stream works is so that it's a piece of ice, and the tongue of it is sort of floating on the ocean. And so the ocean is pushing it up and down with the tides. And so there are these tidally modulated slip events. Those are the dots there on the tide, where it suddenly slips forward by 0.5 meter. Once or twice a day. So that's pretty cool. If you want to understand how earthquakes begin, you want to go someplace where they happen a lot, right? And so our former student Grace Barczyk did in fact spend a bunch of time in Antarctica with my colleagues, and I've never been to Antarctica. I want to go. And what she found is that these big slip events on the ice, if she put GPS instruments out there, oh, sorry.
Just want to go back one slide. It's an astronomer question. Are those neap and spring tides we're seeing in the
Yes.
modulation? Oh, okay,
Yeah.
that's what that was in the previous slide?
Yes.
Okay.
Exactly, it was the fortnightly tide. And so what you see here is she had GPS instruments on out on the ice right where it floats up over the ocean. That's the orange dot. And the blue was 50, 60 kilometers away up ice. And it was known from previous seismic data that these slip events began in one of these two places. That they started slipping fast and radiating seismic waves and sending off those waves into the earth in one of these two places. What Grace noticed is that although the rapid slip sometimes starts where the blue line is, where the blue dot is, when that happens, those events actually start slipping at the orange place, 60 kilometers away. Well, that's weird. And then, so they slip slowly, 60 kilometers away. There seems to have some sort of slow slip communicating in, and then it sort of slips fast where the blue dot is, and that's when the seismic waves get sort of radiated out, and we would call that an earthquake or an icequake. And the same thing can happen in reverse, that you have some events that start slipping quickly at the orange dot, but start slipping slowly at the blue first. Well, that's pretty neat. So that is telling you, at least on this system, there is a slow slip precursor. You can predict these based on instruments, and they're sweeping in, but they're not starting to slip where the earthquake happens. You actually have to go look somewhere else. And that turns out to be a pattern for the Willands ice stream. It's a weird one. And it's giving you a strategy on how you might want to think about looking for those slow slip precursors of the earthquakes. So how can this be? Well, I'm going to just give you a little bit of a cartoon. What we think is that the ice stream is sort of heterogeneous, like the Rotten Fault. It has bumps on it. Some bumps concentrate the stress. Some places are weak. The fault starts slipping where it's weak in general, where it's easy to get over the friction. But because it's weak there, it hasn't accumulated a lot of energy. The bungee cord hasn't stretched very much. And so it sort of putters along slowly until it hits some strong spot and then releases an earthquake. So now we're starting to move here. That this is in a heterogeneous fault, and I'm going to say that I would expect all faults of the Earth to be at least as heterogeneous as a glacier. We might actually be able to make some progress. We're starting to know what to look for. So I'm going to end there on that cliffhanger. And I'm going to let me recap a little bit. And it's been quite a journey. Let me sort of recap where we've been. I've given you 4 different approaches to the earthquake problem of when's the big one happening, or when do earthquakes happen, earthquakes in isolation, and we learned stuff. We definitely learned stuff there. We learned about the friction of faults and how to think about faults as earthquakes as physicists. We then started to think about earthquakes as geologists and realized that not every fault in this world is the same, and that based on the maturity of faults, we get different speed earthquakes and different numbers of aftershocks. We looked at earthquakes on fault systems, and then we started actually being able to statistically, as a population, predict earthquakes. Not the ones we care about, but hey, we predicted something. And we also were able to learn that triggered earthquake rates are proportional to the dynamic strain. That was a mouthful, but that we can start to probe how close to failure faults are. And then finally, we looked at earthquakes in their systems, in their sort of native habitats. And the ice stream is different. The Seattle fault is different than Chile, is different than Tohoku. And that information matters as well. These earthquakes in geological systems. And also philosophically at the end, we ended up using these tidally triggered events where we knew a little bit extra because the ocean loading is making the earthquakes. that sort of gave us this beautiful natural experiment, much like the seismic waves triggering gave us a beautiful natural experiment where we could start to really learn something. So, the earthquake problem, when will we have earthquakes? No, I didn't answer it, sorry. But at least, hopefully, I proved to you that it's not a hopeless question. This is not a waste of time to study it. We actually have meaningful ways to make headway. And my current project focuses on the power and context of a natural experiment. I think these natural experiments are very important. And I just got back from my 4th trip to Chile in the last year and a half, where we are trying to develop a project to instrument the system properly in a system that we know is extremely active and potentially has this precursory behavior. And we want to get those instruments offshore, where the faults are, where the interesting stuff is happening, long term. And we want to try to develop, this project's called SC4D, it stands for Subduction Zones in 4 Dimensions. We want some time. The 4th dimension is time, and we want to be patient and have instruments in place so that we aren't guessing about what our data means in the future. I will stop there, and thank you all very much.
On the point of questions, do we have questions from the online group? It seems fair to introduce those at this point.
Sure. So, Emily, this is probably going to surprise you, but a number of people in the comments asked in a variety of different ways, essentially, when will the big one happen? Someone asked this question literally the second the Zoom room opened at 6 o'clock. That was the first question immediately was asked.
I'm glad I know my audience.
Yeah, exactly. So I think maybe the better question to ask is sort of, what would we have to know in order to know when the big one would happen? So if we don't know now, like what would we know? And I want you to answer that question both in terms of answering it 10 seconds before the earthquake happens and 10 days before the earthquake happens.
Why did I ask you to do this, Will? All right. Well, let me also answer the question decades before the earthquake happens. You know, so there is a strategy, which I didn't give much time to today, but it's certainly a valid strategy, which is to go in the geological record and map out when earthquakes happened centuries or millennia ago and try to figure out the periodicity of the system. And because earthquakes interact a lot and faults talk to each other, as we just saw, it's not going to be a clean, prediction, on next Tuesday, 300 years from now. But that is a strategy. And using that strategy, we do get recurrence times on the San Andreas, for instance, of a few hundred years. And so we are moving into the window when we might expect something on the northernmost San Andreas, a repeat of 1906. We're kind of just moving into that window. And we are way, 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 way overdue on the southernmost San Andreas relative to when the last one happened. The southernmost San Andreas is from sort of Paso Robles down to the Mexican border. So that's that. I should say that. So when the big one's going to happen, any day now. The 10 days before, who knows? We don't know. Personally, the path that I am running after is looking at slow slip on these slow motions of earthquakes, whether or not that will bear fruit. Some science fails, but that to me is the most promising route forward. And if we could actually observe this consistently before multiple earthquakes, that would be the route forward. 10 seconds before it happens, that's a triggering problem. And so that's a question of asking how earthquakes interact, and knowing at a finer level that population I showed you of earthquakes triggering earthquakes and being hit with seismic waves, whether or not we can refine that enough in a particular region with a particular specificity that we could make something useful out of it. I should also point out, particularly for the Zoom audience, there is another strategy called earthquake early warning, which is not prediction. The earthquake has already happened, an earthquake early warning. And the idea behind earthquake early warning is it's very much like lightning has already struck and you have not yet heard the thunder. Electricity goes faster than thunder, it goes faster than sound waves. So if you can very quickly know when the earthquakes happen and locate them, you can send a message on all of your cell phones, and you guys probably got one not that long ago, that outpaces the seismic waves, and that's called earthquake early warning. And so that can give you a few seconds warning, depending on the geometry.
Okay, I have a question, Emily, by and for the non-experts here, about the triggering mechanics, which is a lot of people, I think, attending this have been in earthquakes. And is it possible for just a regular person to, based on what kind of earthquake it feels like the kind that sounds and feels like a truck hit your house, you go out, no truck, and then the long rolling type or the really jittery type, could a person be able to have a sense of what the aftershock picture might be based on that?
Oh, that's a place I didn't realize you were going to go with that. That's an interesting question. And I think I'm supposed to be sitting here.
That's okay.
Yeah, the butt seismometer is pretty good. I certainly can tell the difference between something that's a local earthquake versus something far away. The rolling ones are the far away ones. I guess you probably could anticipate if it's a rolly far away one that you're going to get some aftershocks, but they're probably going to be not as close to you. And if it's a really sharp one, it probably will have more aftershocks close to you. I think that's legit.
See, there is a prediction capability.
Yeah. Well, we can predict aftershocks. We do a great job. Nicholas van der Elst, who I was just showing his PhD work, his job now for the U.S. Geological Survey is to predict the aftershocks. I mean, he does it for a living, and it's not terrible.
Okay, we have a question.
With the global warming and supposedly the water raising and there being more water, is that making it better or worse, or what's the impact of that?
To the best of my knowledge, global warming effects on sea level are not impacting the earthquakes directly. There is some effect because it's still the same mass of the ocean, it's just expanded or not. So if the weight of the water matters, expanding or contracting the ocean is the same weight. That said, melting the ice sheets for sure affects the earthquakes. And we do see the unloading of the ice triggering a bunch of earthquakes around the margins of major ice streams. We see it in Greenland. It's to be expected.
Okay, we have a mic over there, then over here.
I want to go back to the Tohoku earthquake. You had a model and the observations. There was a striking difference in sharpness as you went down in depth. It was much sharper for the real system than for the model. Is that significant?
I think it's probably the quantization of the data. I think there was a bad sensor in there at that depth. Yeah. I thought I was pretty happy with a fairly simple diffusion model. The other explanation is the rocks have layers and they have different ability to transport heat. And so I used one heat transport coefficient for the whole thing, and in fact, it's a layered system.
So we hear stories of animals detecting earthquakes, which indicates that there is some sort of signal coming from the earthquake to which the animals are more sensitive. And presumably, we could develop machinery to detect those same signals coming out as an early warning mechanism. So any thoughts about that?
I try to stay far away from biology. They're hard. Studying animals is hard. So it's really hard to know whether or not those are robust observations because biology is hard. There is sort of a theoretical possibility that animals can feel foreshocks. Their butt seismometers are pretty good. And we do know foreshocks exist for a very large portion of earthquakes. That is the statistical model where I keep saying we can predict aftershocks. Statistically speaking, some of those aftershocks are likely to be bigger, rarely, but occasionally bigger than the original main shock, and then the aftershocks now the main shock. You with me? Okay. So then we call the original aftershocks, we now call them foreshocks. And so it is possible the animals can detect that kind of foreshock sequence, and that would give them information. We would get the same place probably more straightforwardly by looking at a seismometer. And we wouldn't have to do biology.
So I have a question. So this is an example of an active earthquake zone in Chile, if I understood it correctly, with high density of sensors. What about installing hundreds of thousands of sensors along, for example, San Andreas Fault? Just overpopulate the whole zone with high-quality sensors and feeding data into these algorithms. Could that somehow help predict?
Perhaps. Seismology in general is not the best funded science out there. And so that is not something we've had resources to do. I'm all for more seismometers everywhere all the time. I think there is a major technological breakthrough that's happened recently, which is the use of fiber optic cables as seismometers. And so fiber optics, that's how the internet runs, these two lasers. And so if you measure, you can probe those fiber optic cables and measure the strain, the stretching of them. And if those could be made available scientifically to the research community, or at least to the government monitoring agencies, that's probably our best route forward to getting more seismometers everywhere all the time. And I have real hopes that that might happen over the next decade. But the problems there are primarily legal and political rather than technical. Will, you had something?
A number of people wanted to ask questions about induced seismicity and enhanced oil recovery and kind of what we know about that, how we can model it and predict it, and what it's telling us about earthquakes.
Okay, so induced seismicity is our shorthand for human-made earthquakes. Yeah, humans can make earthquakes, either through pumping groundwater out of the Central Valley, or through fracking, or through wastewater injection. Anytime you pull any fluid deep underground, either in or out of the earth, geothermal power, all of those make earthquakes. We've known for some time that that's possible. You kind of think if you could be able to predict anything, you ought to be able to predict those. We've made some progress. Oklahoma was useful. During the fracking boom in Oklahoma, there were really a lot of earthquakes, and I'm sorry for the people of Oklahoma, but from the scientific point of view, we did make some progress. I don't think I would feel comfortable saying we could predict earthquakes, any individual earthquakes, but we're getting better at predicting rate of earthquakes from those situations. The big unknown there is some places are very sensitive, appear to be close to failure. You pump a certain amount of water in and the earthquakes happen. Others are not like that. And we have not been very successful thus far in being able to tell you before you do it which ones are which. Once you're going, we can correlate the earthquake rate to your volumes of water in and out of the ground. That can work sometimes. But before you get started, that's harder. Maybe Texas will give us the answer. Seems to be popping now.
I think we have time for a couple more questions. There's one here and then one over there.
Okay, so you didn't tell us on this diagram what type of sensors they are. I don't know if they're GPS sensors or seismometers, but I'm just wondering.
Yes and yes.
Yeah. You must have a network of GPS sensors all around faults, right? And you know that sort of out in the field, far away from the fault, you know how quickly the plates are advancing. You told us centimeters per year or something, right? So I'm just wondering, like, as you see the deformation as you get closer to the fault, if you can use sort of the slowing down of that propagation to measure the coefficients of friction and those parameters that you need. Like, what does that tell you when you look at GPS data?
Oh, there was a lot in that question. Okay, so first of all, let me be clear. This is a proposed project. It does not exist yet. SC40, I'm running back and forth to Chile to try to make it happen. So this is what I think we need to do to answer the question, but we're not there yet. In general, we do often in places have GPS and or seismometer networks. We can, through that slow motion, we can often determine where a fault is locked versus where it's not locked, where it's moving slowly versus really stuck. And so that is giving you some information about where you're accumulating energy that can lead to an earthquake. So for instance, the middle part of the San Andreas, between about Watsonville, really just south of Watsonville, and Paso Robles, is actually creeping. It's moving all the time. That's why I said carefully. Most of the San Andreas isn't moving most of the time. That's actually keeping up with the plate rate, which is why we think the most likely scenarios in the San Andreas is a northern rupture or a southern rupture, and some deity ought to help us if they both go at once. So there is a lot of information, spatial information from that GPS data. I can talk to you for a long time about it after the talk, but the short answer is, yeah, there's a lot there.
Yes. Could you please expand upon your answer about climate change? And I'll be specific. The question came up on a online forum probably 5 or 10 years ago. And since I'm a chemical engineer and electrochemist and not a geophysicist, it sounds like I gave the wrong answer or put forward what possibly could be an answer. And the question was, is the change in sea level going to cause earthquakes? And my answer was, the ocean is thousands of feet deep. Even if we add 5, 10, 20 feet of sea level rise, in terms of a percentage, the hydrostatic pressure that column of water is exerting on the Earth is very small as a percentage. And so I said, I don't think it's going to make that much of a difference. Why was I wrong?
You were both right and wrong. You're wrong because faults are capable of making earthquakes with shockingly small stresses. The stresses in those seismic waves that came from Alaska to Montana were, much less than an atmosphere of pressure.
Oh, okay. So,
Okay.
yeah, a lot less than 10
So
feet of water.
if a fault, and there are so many faults in the Earth, and there are at so many different places in the cycle, if a fault is close enough to failure, you can make, butterflies flapping its wings can in fact make earthquakes. Just rarely. It's a statistics thing again. On the other hand, adding water to the ocean, if you actually add water from the ice melt, sure, that does affect the loading and that would affect things. If you're just expanding the water, that's not a change of mass.
Thank you, Emily, for that fascinating lecture. Thank you all for coming tonight. This is the last lecture of this academic year, but watch your email for in the fall for next year's schedule. Good night, everyone.